Okay. It's quite amazing that Chinese students obey the notice from the school. Anyway, so let's do that. Or they're just sleeping. Anyway. Oh, people are coming. Okay, so the last time we talked about killing horizon. So killing vector. So last time we considered the killing vector, and which satisfy like this way, and then we consider the normal, the no hypersurface, and we consider new hypersurface n, which is defined by the new hypersurface where the killing C mu the killing vector satisfy the following condition. Where copper is surface gravity, here, so it's called at the n. At the n is called killing horizon. Okay, killing horizon, and then killing horizon. Then we consider but C mu needs to be properly normalized. In such a way that normalized such that the C mu, C square, goes to r goes to infinity is -1. So that's the normalization we would take. So that's the normalization we would take. So this C square is just C mu dot C mu. Okay, so that's the case. So that's the normalization, and this surface gravity, so this copper is sensitive to this normalization. Copper is sensitive to this normalization. So that's the case. And then last time I just did some stupid way of introducing acceleration. And then I made a mistake in the normalization, so I will recap the previous lecture, which I failed to keep like an anyway. In comprehensive manner. So what we want to do is we want to give this classical interpretation to the surface gravity interpretation, which is in fact the surface gravity is the acceleration of the static particle near this horizon measured at infinity. Measured at infinity. Spatial infinity. So this is a classical imputation. So let's review that. So how do you define? So this is the case. And we just have the unit mass, this particle, and then you just connect the string in between, the observer infinity, and then the unit particle with unit mass, and then the force. Field at the infinity is in fact acceleration. And to define acceleration mu, so first of all, so this observer has the u mu. The vector u mu is just properly normalized, minus c squared c mu, like this way, properly normalized one, so that the u squared is equal to -1. So that's the case. And acceleration is just a mu divided by d u mu d tau. So d tau. So this is the case. So this is the ordinary. So that unfortunately not so many people, students came to this class. But some students asked me how do you define this mu? But this is a vector, and it's one more derivative with respect to proper time is the acceleration. This can be written, I think mu. So this is acceleration. So, okay, and then, so let's compute this one by using this one, and then, so this can be written, yeah, I think I should write down dot, like this way, dot, and then, minus, like this one. Okay, so the first of all, so you just write down that u as this is equal to c dot c mu minus c squared. So no, this is not true. C mu like this way. Okay, like this way. And the down mu acts on numerator will give you first term. Down mu acts on denominator will give you the second term. And you will notice that this one is 0. This is 0 because this can be written as this c dot delta. This is 0 because c dot nabla. Now square is like something like a 2 times c nu down mu c mu, like this way. Yeah. So c square, and we know that this is a Killing vector, so that if you make it symmetric, you get 0, and since mu and nu are symmetric. So this will, by using property of Killing vector, this is 0. So this is gone. So the acceleration is given by here, and then so this can be written as the something like partial mu. So this is acceleration you will get. So therefore, this acceleration is just log of this normalization vector of the length of this the Killing vector at the horizon. But so far, so this calculation so far is nothing to do with at the horizon. So we don't restrict ourselves to the horizon. This formula is all true, even inside any particle in this region. So this, if this is a U like this way, U is inside a, how to say, outer of the horizon. It's totally okay. This formula is valid because U is just some proper normalization killing vector. And then again, so this at this moment the C mu is something like a partial T mu. You can consider like this way. So I will see this one as the example of the Shashi. Okay, and then so you have to make it properly the okay. And measured at the infinity, infinity is measured at infinity is the sorry. So for instance, acceleration A is a square root mu. It's just normalization. This normalization, which is square root mu and mu. Okay, and this is equal to So on the other hand, so acceleration at the measured at this point is this one, but the measured at infinity is you have to multiply redshift factor, and redshift factor is simply like this way. So this is the redshift factor. So this is measured at infinity. At infinity, this one is measured at locally. Acceleration. And as we will see, actually, in fact, in the space and this is divergent. In fact, divergent at the horizon, but this redshift factor it becomes 0 when you go to infinity. So that they counter and then you get the finite value. So that's the case. And then to compute this one, we just do the following thing. Okay, and then so this guy, so the second term is 0, and then first term is at the horizon, H. Maybe I call it killing horizon H. So and I call it this one is H. This horizon at the H. Okay, you can use this formula. So therefore, this one is equal to kappa C mu minus C squared. Okay, that's the case. So therefore, if you just compare between these two, infinity is equal to square root minus C squared, and then kappa C mu kappa squared divided by minus C squared. Okay. And then take square root. Okay. Sorry. So like this way. Sorry. And this is equal to square root kappa. Square is equal to kappa. Okay. So that's the formula. Sorry. The last time my introduction of I used something like I don't know, kappa square is equal to minus 1/2 del mu C mu. Last time I introduced something like this one, right? Mu del mu C mu. This one is not necessary actually to introduce to talk about the acceleration is equal to kappa. Okay, so this is exactly the at the horizon. Okay. So here from here to here. One has to use the property of horizon, okay, of the killing horizon. Okay. So that's the part I failed to explain last time. So, okay.
A is invariant quantity, right? Here, the A.
this A?
Yes.
What do you mean in
Scalar.
scalar? Yes, yes, yes,
Which
yes.
is invariant quantity, so it should not depend where we are measuring it. It should be the same, like a proper time. It should be invariant.
I'm not sure, to be honest. But it's a scalar, but it's just the normalization of the, how to say, acceleration vector, right? Acceleration vector. And then you really need to, how to say, so properly normalized by dt d tau 1/2, which is this guy. So, I mean, how can I explain that? So it's a scalar quantity, but it's just the length of this acceleration. So you can just, you have to normalize the thing for the redshift factor. So otherwise, I mean, this guy is really divergent. It's really divergent at the horizon. So which I'm going to talk about. So for Schwarzschild, okay, and then Xi square can be understood as the Xi mu can be understood as the del T mu, or del V is also okay for in the Eddington Finkelstein conjugate. So therefore, a mu is something like a partial mu log 1 minus 2m over r. Okay, 1/2 from this formula, from this here. Okay, and which can be written as follows: the m over okay. And this is only like non-trivial when the mu is, so it's a really spatial. Mu is equal to r. Sorry, I think I should write the bottom. Mu is equal to r. Spatial component 1/2 is equal to, this one is equal to m over 2m over r. Like this way. So this is a non-trivial guy. So therefore, the norm of this one is just a mu. So A is equal to, like this way. And then, so this is equal to m square divided by r square, 1 minus r to the fourth. R to the fourth, 1 minus 2m over r. Okay, and the square root, which is equal to m over r. So this is the acceleration measured at the locally, but as you can easily see, this goes to infinity as r goes to infinity. Okay, r goes to infinity. No, r goes to infinity. 2m. So it's if it goes to horizon, this will become divergent quantity. Okay. Okay. So this is divergent quantity, but if you multiply redshift factor, So dt, dt d tau square divided by 1/2 is equal to 1 minus 2m r. Sorry, I think I should be square here. So in the Schwarzschild, it's like this way. So this is a redshift factor. Redshift factor, if you multiply it, so therefore infinity is the m over r square at r is equal to 2m. Okay. So r is equal to 2m, so which is equal to let's see, 1 over 4m. So this is the surface gravity of the Schwarzschild. So that's how you define the acceleration at the horizon, measured at infinity. So that's the a calculation. This is, I think, okay. That's the identical to what we found by just ordinary definition of this one for Finkelstein, Eddington-Finkelstein ingoing metric. So that's the recap of last time. And then I'm going to move on to slightly talk about so-called Rindler spacetime. Okay, so Rindler spacetime. Okay, so to understand this phenomena a bit better, so we would talk about the linear spacetime. Linear spacetime is kind of like some part of the flat Minkowski metric. So like consider the 2D Minkowski, which is something like a ds squared minus dt squared plus dc squared. Okay, and then we can just take the following the change of variable. T is equal to zr since kappa tr, and then c is equal to zr cos kappa of tr. Okay, so in this case, t and then z are literally minus infinity to infinity. But here we just restrict ourselves the tr is the infinity to minus infinity, but zr is indeed equal to infinity. Is the positive quantity. Positive quantity, so that the t can be negative, but the z has to be positive, positive region. Okay. So then, so here the metric will become like this way: is equal to minus kappa can be written like a zr square, and then the tr square. Like this way. So, and this is called Rindler metric. Okay, so this is called Rindler metric. Okay, and the reason why I call it this kappa is you will see from now. So kappa is related to surface gravity from now on. Okay. So from here, you can easily see that the z. So from here, so the t and z are related by like this way. So from here, T and Z are related like this way. Okay, so therefore, not only that, so therefore, if you write down the Penrose diagram, so that's the region we are interested in is so if you write down the Penrose diagram for this one, so I think usually you just write down like this way, B and U, and then diamond is here. Okay, diamond here, and then of course the I mean U and V are related by U and V are like a tangent inverse of what we already learned. I already forgot which one is T and then Z divided by 2, which one is divided by 2, which one is plus or minus? I already forgot. Minus and plus. Okay? So like this way, so this is a Penrose diagram for the Minkowski space, but for the region which satisfy this condition, this one and this one. Okay? So it's in fact in here. So this region. Okay, and then this is a TR is constant region. Okay. Like this thing. So these are the TR constant region. No, TR is no, ZR is a constant region. Sorry, ZR is a constant region, and then TR is a constant region is something like this way. Okay. So these are the so here is the Rindler spacetime. And how is it related to the black hole? Well, for instance, short is you can zoom in to the close to the horizon. Close to the horizon in a short shot. In a short shot. So let's write down short shot in the only the looking at the dt square plus this inverse dr square. And I forgot about this omega two sphere part. And here we zoom in into near horizon region. Okay, near horizon region. So at the r minus 2m, I call it x over x square 8m. X square over 8m. Okay. Then just rewrite the metric. So to rewrite the metric in terms of x square, x, so therefore 1 minus 2m over r is in fact equal to kappa over x divided by 1 plus kappa over x. Okay. So can you see that? Can you see that? So okay, maybe I should do that. So 1 over 4m, and r minus 2m. Sorry, square. So 8m. No, sorry, 4m. What I'm doing here? Yeah, I'm doing stupid. Sorry. So kappa x square is equal to x square is the 1 over 4m square x square, which is equal to 8m divided by 16m square divided by r minus 2m. Okay, and this is equal to 1 over 8 r minus 2m. Okay. No, not 8. Sorry, I think I'm too stupid. Okay, so like this way, 2m. Sorry, 2m. Okay, so okay, so 2m means it's the r minus 2m minus 1. Okay, so this is the case. Is it okay? Do you agree with me? My calculation? Let's see. This is 16m squared, and x squared is the 8m r minus 2m, so it should be okay. And this is 2m, right? Okay, so it's okay. So therefore, this is r minus 2m minus 1 divided by, so plug into here, you get the r over 2m. Okay, so therefore this is 1 minus 2m over r. Okay, so is it okay? Everything's okay, right? Fine.
What you are proving here is that the value of k is 1 over 4.
Yeah, I use the fact. The kappa is 1 over 4m.
But in generally, we have to derive the value of kappa from this equation.
From this equation, yes, that's true. So how to move into the horizon. Yeah, you're right. And then, so when x goes to 0 limit, this can be just roughly speaking, you just write down r is roughly kappa of x squared. And so therefore, what we have is ds squared is equal to minus kappa x squared plus the dx squared. So dx squared, so that's the case. So because dr is equal to 2x divided by, so using this one, dr is equal to dx divided by 8m, right? Which is equal to kappa dx. Okay, kappa dx. So therefore, dr square, and this is equal to kappa x.
What should be x as well, right, in the numerator?
You're right. So 2x. Thank you so much. Kappa x dx. So this is equal to dx squared. Am I doing something stupid? I understand, minus 2. Yeah, minus 2. Okay, so that's the case. So therefore, this metric written here, can be written as like this way. Like this way.
This would be dt or some.
Thank you so much. dt squared plus dx squared. Plus dx squared. And this is exactly what we found over there. Okay, what we found over there. Okay. So found here. So therefore, 2D integral space wants to zoom into the near horizon limit. Okay. Okay, let's do the manipulation of what we are doing. So for instance. So, for instance, in this coordinate, so you can just introduce like a classical type coordinate, which is u is equal to minus x e to the minus kappa t, and v is equal to x e to the kappa of t. Like they said, this is a classical type coordinate, and then this metric. So if you introduce this one, du and dv. So du and dv, which can be this. So like from here, du is equal to what was that? I have to do the calculation. Let's see. So let's see, du is equal to minus dx e to the minus kappa t dx plus x, so minus x. I'm not good at this kind of calculation. Okay, I think plus kappa x e to the minus kappa t dt. Okay, so do you agree with that? And then dv, from dv is equal to e to the kappa t dx, okay, plus, and if you ask on it, so you have a kappa x e to the kappa t dt, like this way. And if you multiply them together, you will get the this result. You get this one. Okay. If you multiply them together, so the diagonal term will give you this guy. Sorry, not this guy, and then I think I missed minus sign here. Sorry. Yeah, minus sign here. Yeah, minus sign here. So if you multiply these terms, you get the dx squared. And if you multiply these terms, you get this term. Okay? And this term. So therefore, it's just an ordinary Euclidean one. So this is Euclidean one as we saw this one. So here this ds squared is equal to du minus du dv up to some component factor. Up to some component factor. I don't remember the component factor. What was the component factor? I already. And this is the cos. According to my note, this is equal to cos u cos b and the plus. But anyway, so that's not important. The component factor is not important. And this is the Rindler-like coordinate. So therefore, you can just see that this is in fact, can be written like a dt squared plus dx squared plus space. That's we did it here. Okay, so this is here we need to use the change of variable u is equal to t minus x, b is equal to t plus x, and so on. And you get the fraction. Fine. And let's see the Killing vectors. Killing vector in the Rindler space. So since the metric is independent of time, so the Killing vector is the so Killing vector is the xc mu is partial t mu, right? Like this. Can be considered this one. And this is indeed, maybe, okay, maybe I should write it down like this way. C is equal to xc mu is partial t. And if you write down the u and b, this can be written as follows. Kappa b del b, and then minus u delta u. Okay, delta u. Okay, delta u. So this is just change of variable. Should I do that? I think it should be okay, right? It's super easy. Delta t is equal to usual practice plus del u del t delta u. Usual practice, and then plug this one into there, you get the kappa, right? Plus kappa. So t derivative will give you kappa times b, and then the t derivative in u will give you minus kappa because there's a minus sign here times u. Okay, so that's the case. Fine. So that's expression, and then you can easily see that from here. u equal to 0 and v equal to 0, it is indeed become null. Is null. So in this coordinate, u equal to 0 is this axis. This axis. This is u equal to 0, and this is v equal to 0. That is null. But that's very, I mean, intuitively correct. But you can easily see that the null, I mean, from here, u equal to 0 means that this vector c is equal to, what was that? Kappa b del b, right? At u equal to 0. Okay. And this is null because of metric is du dv. Okay. So therefore, if you take c square at u equal to 0, this is 0. Can you see that? Is it okay? Since du dv, so the only metric is non-trivial, du dv is equal to -1. But here you only have a b component, so therefore dvv is equal to 0. Okay? So therefore it should be 0 at u equal to 0. So therefore u equal to 0 is null, no hypersurface. The same thing apply for the b equal to 0. The b equal to 0 here, b equals 0. So that is also no hypersurface. Then we can ask ourselves, is it the killing horizon or not? Okay. And then to see the killing horizon or not, we just need to understand that this killing vector c dot delta c mu, how it behaves. Okay. How it behaves. So at the u equal to 0. So at the u equal to 0. At u equal to 0, so this is literally this kappa b del v acts on kappa v del v. Okay, so this is xi mu, and xi dot nabla is this guy. So therefore, if you act on it, you get the following: kappa square and v del v. And this is equal to kappa v, xi mu at the horizon, u equal to 0, killing horizon, or u equal to 0, no hypersurface. So therefore, in the Rindler space, the u equal to 0 is a killing horizon. Horizon at the surface with surface gravity kappa. Okay? Surface gravity kappa. So that's the conclusion. And the same conclusion can be applied for v equal to 0. So v equal to 0. So this u equal to 0 is this yellow one. So therefore this is killing horizon. With kappa. And the v equal to 0 is this the other horizontal diagonal line, and this is also the killing horizon. Killing horizon with the surface gravity kappa. I mean, you can do the same exercise. I mean, xi mu at the b equal to 0 is something like a kappa. What was that? B, no, not B, U, del U. And you do the same exercise, you get the same answer. Okay, so that's the case. Most likely I'm not correct. So with surface gravity, is the kappa or minus kappa? It should be kappa, but I'm not confident. Okay. Sign, I'm not sure, but it should be positive. Right? it should be positive. This one, to be honest, I'm not sure. I think it should be copper. I think I make a mistake somewhere in the plus minus. I don't know which one is correct. Can you see easily? So sorry. So this not this one. This one is plus minus. I don't know which one is correct. Can you see which one is correct? It looks to me minus kappa if you do an honest computation. Because I mean, it just have a minus kappa u del u, right? Minus kappa u del u. In that case, you should get the minus kappa. Seems like that's the case. Okay, it seems like a minus kappa. Seems like a minus kappa. But the meaning is no. I don't know. When you take absolute, since the absolute value somehow sign can be negative as acceleration. Acceleration needs to be positive, but the surface of gravity can be negative. If you go to the other side of the other spacetime, I don't know, to be honest. Anyway, so only, let's forget about the say v equal to 0 case, but if you look at only u equal to 0, xi mu, so this is the killing horizon, and the surface gravity is kappa. Okay. So that's the case. Okay, and here, so the killing vector, so c square is indeed equal to the kappa x square minus, right? Yes. And then this goes to infinity or minus infinity as the mass x goes to infinity. So therefore, it's not properly normalized. So no natural normalization in the normalization in the Rindler space. It just because Rindler space. I mean, it's just because we just zoom in this Schwarzschild horizon. So we take the r minus 2m is equal to x squared divided by 8m, as far as I recall. Since we just move into the near horizon region, so the normalization, so since zoom into the near horizon region, so we somehow, at the cost, we have to lose the proper normalization for xi. But it's the somehow nature of the Rindler space. And then if you just consider mu, the acceleration of this guy is in fact equal to, acceleration is the xi, how do you, it's 1 over u del v plus 1 over v, 1 over v, and del u, delta u. Okay, how do you get this one? Sorry, how do you get this one? I think I have to do the correct way of. Okay, how to get this one? So that the mu, okay, mu is something like mu is something like 1/2 del mu log minus xi square, right? Okay, And then what we need to do is just compute the inner product of C squared. So which is something like C squared minus C squared. In this case is kappa squared times this cross term will give you the non-trivial result, and the minus sign will cancel with the metric UV. So this is the case. Okay, so therefore 1/2 del mu log of kappa square UV. Okay. Okay, so that's the case. And then let's do the computation. Maybe I can just move here. I hope I'm not gonna make a mistake. So therefore this is equal to, so therefore AU is equal to something like a So how do you do that? Is this kappa square UV divided by kappa square V? Is it the case? Am I correct? Right? Do I look? Am I correct? Is this okay? And V is equal to kappa square U divided by 2 kappa square UV. And this will give you 1 over 2P. And this is equal to 1 over, what was that? 2U. Is it okay? Do you agree with me? Is it okay? My computation. It should be okay, right? Yeah, so far it's okay. Yeah, I think that the best way to, yeah. It's okay, right? So A mu, dx mu is something like AU du plus V dV. So therefore this is equal to du 2u plus dv and 2b. Okay, so that's the case. Okay, and then to go from here to here, so you have to do the inverse metric. So metric is something like so at this moment metric is something like g mu nu is equal to minus 1/2 and minus 1/2, 0, 0. So therefore, upper, the inverse is something like minus 2, sorry, 0, minus 2, minus 2, 0. Is it okay? So therefore, this 2 will cancel, and since it's cross term, you will get this guy. Is it okay? Do you understand? And ds squared is equal to minus du dv. So therefore, the metric here is minus 1/2, minus 1/2, 0, 0. And the inverse metric is the off diagonal minus minus 2. So therefore, I mean, so AU del del U, so this is mu, is the plus V del del V. And then since to make it U up, we need to use this guy, and which is the this guy. So therefore, so this times 2. So therefore, this is 1 over V del del U plus upper V is the 2 times this guy. So therefore, the del del V. So that is exactly this guy. Okay, so this is acceleration in the Rindler space. So this is acceleration vector of the Rindler space of the observer in this time-like killing vector. And then again, a normalized one is the a mu square root, and then this is equal to I mean it's just multiplication of this guy. It's just multiplication of this guy is equal to minus 1/2 uv square root 2, and then ub. Where did I erase? Seems like I erased. uv is indeed equal to, so this is 1 over x. Okay. And again, so this is divergent as you go to the is infinity when x goes to 0. So as you move into the horizon, killing horizon, this goes to divergent. But if you properly normalize the d tau, properly normalized acceleration is how to say, the d tau. So a infinity is d tau dt 1 over x 1/2 I mean 1/2 kappa x. No, I think dt d tau. Yeah, dt d tau. It should be okay. X 1 over x, and this is equal to kappa. So acceleration measured at infinity is you have to multiply this redshift factor, and then you will get the final result at the kappa. Okay. So therefore, it's consistent with what we have in the Rindler space. What we just computed is just zoom into the cross short, and they do the computation. We have a consistent result. So that's another way to derive what we already have seen. That. Yeah.
Why do we need the Rindler space-time?
Because I mean Rindler space, this is closely related to Unruh effect and so on later. So I mean we don't need to use the Rindler space, but I just want to talk about the Unruh effect later. And this time-like geodesic, time-like killing vector is have acceleration. This acceleration and this one, this acceleration. And this kind of like an observer will receive some kind of like a particle creation later and so on. So therefore, this kind of observation is later become important. That's why you just introduced Rindler space here. So this is later purpose, and also like an easier way to look at what's going on in the Schwarzschild.
It's simply 2D Minkowski, right?
Yes. 2D Minkowski, but somehow with an accelerated observer. Later we'll receive like there's an Unruh effect that even in Minkowski spacetime, if you have acceleration, you can see like a particle creation and so on. That's one of the effects we will see later. That's the Unruh effect. But this is the preparation for this one. I just want to introduce this one at this moment. Okay, good. Okay, so then I can talk a bit about there's something called bifurcation. So there is something going on here. So it's a cross section of the King horizon. Okay. Okay, so here, delta V. So in this, I think I will use the other color chalk. Oh, this red one. So here, there's a vector field. You can consider no vector field, no vector field. So here, at the horizon, so this C mu will become kappa B delta V. Okay, but it's a U equal to 0 horizon. So this is the vector field B delta V, and of course when B equal to 0, eventually become 0. At this point, maybe it's better to write that bigger. So you have a space-time like this way. B and U, and King C is something like so inside, so in the interior of the Rindler region, so the C is something like this way, and the vector field is something like C mu, which is kappa B delta V minus U delta U. Okay, delta U. But at the Killing horizon, U equal to 0, so this become like this way, so which is the kappa B delta V. Okay, so this U will be gone. So the vector field is become bigger as you just B grows, so because it's proportional V. But as you move towards the origin, it become very small. The become something like okay, maybe I should write down like this way, very small, and at the end this becomes 0. Okay, the vector is really around here. It's really long. It become really long, like this way, like this way. That's the vector field we will have at the Killing horizon. The same thing happened here. So around here, Killing horizon. I think now I understand why I make a mistake. Surface gravity here. I think for here, Killing. So this is only. Okay. Now I understand. Now I understand why I get the minus kappa. I mean, if I use, so you cannot define how to say, you cannot define the surface gravity here by using this Killing vector. Here you have to use Killing vector like this way. The other Killing vector C prime. So this one cannot be simply naturally extended to here. This C prime is indeed equal to kappa U del U minus V del del V. Okay. Sorry. So the U and the V plays a opposite role in this region. Okay. So therefore, this direction is indeed U delta U kappa. So therefore, it's okay. The plus sign. So this is plus sign. Okay. Sorry. Now I understand. Okay. So that's the case. That's the case. But these are not affine parameter. Affine parameter. So the kappa V is not a fine parameter as far as I recall. Sorry, V is a fine parameter. Yes, sorry. Yeah, V is a, sorry. This. Okay. Now, so recall that this V is related by e to the kappa small v. And then there's something going on here. I don't print that part of the lecture note. So let me look at the lecture note. Sorry. There's a, when you define the yeah. It's okay. This is okay. Small b and the capital B, when you define the classical type coordinate, we have it like this one. Okay. Okay. So therefore, so this C mu is indeed equal to delta small b, in this region. So this is equal to kappa b delta v. And we know this is not the, this small b is not a fine parameter. So because I mean here C mu, C dot nabla, C mu is the kappa C mu, right? So this is not zero. Okay. Right hand side is not 0. So even though this is geodesic, but this C dot nabla does not give you the 0. So therefore, this coordinate is not a fine parameter. On the other hand, if you parameterize K, is the C, mu, and they're related by what? They are related by kappa. They are related by kappa e to the kappa b x c mu. If you just normalize like this way, in fact, this will satisfy. This will satisfy. This kappa is so okay. So this is kappa b. So therefore, the k dot nabla, sorry, k mu is equal to 0. Okay. So this will be satisfied. Okay. So this this k is indeed the vectors which is affinely parameterized. Okay. And in fact, this k mu can be written capital B. Okay. Capital B. It's not small b. So therefore, it's really constant. It's really constant. This is kappa. It's really constant. Everybody, so it's really, the length is this vector field at the Killing horizon is really constant. The constant value. So it's just a unit vector in delta V. So this is delta V. But this red one is the delta small b inside of here. So therefore this small b is not a fine parameter in the horizon, Killing horizon. The capital B is the affine parameter. Okay. So that's a relation between them. And what's important is that they are here at the bifurcation point. So bifurcations, okay. So here in Schwarzschild, this will become S2. At this point, Killing vector is all vanished. So this C mu at the point, let's go, this is B, bifurcate, B is equal to 0. C is equal to 0, because I mean it's proportional to V del V, right? So this V becomes 0 at this point. The same thing happened in the other vector. So U delta U becomes 0 at this bifurcation point. So therefore bifurcation surface is defined at it's the codimension 2 surface is defined at this property. So that's the bifurcation point in the and later so this bifurcation surface at the Killing vector becomes 0 is very important role in the case of the zeroth role of derivation of zeroth role of thermodynamics. Okay. So that's why I introduced it. So important thing is this, as I mentioned. So this C mu is the some kind is the Killing become null at the Killing horizon. Okay, no horizon. No or tangent to this Killing horizon or tangent. This Killing horizon, but it's not a fine parameterized because it's just proportional to kappa, this equation. But you have to go to the affine parameterized vector, you have to do the proper normalization. Okay. But because it's not normalized affine parameter, so it becomes the point where the Killing the C become banished. That is called the bifurcation surface. And this will play the role of the slope. Okay. Let's take a break. Yes. Any question at this moment? is the people. Okay. Only 4 will join as the online. Okay. Anyway, it's recorded. It should be okay. Let's take a break. And move on to. I will move on to Raychaudhuri equation from now. So except people in Simis, you guys are living nearby, right? Just around the campus, right?
No, I live in Handan.
You live in Handan? Ah, I see. Then it's coming here is kind of trouble.
Not much, because the rain was not that severe.
Yeah. It's getting stronger, but it's still manageable. Still manageable. I think the school made a too early decision. So how do you usually commute here?
By bus, shuttle bus.
Oh, by bus.
School bus.
Oh, I see.
四维的面的。
Oh, by the way, next semester somehow, first I was assigned differential geometry course next semester, but they somehow school changed their mind, so I will teach conformal field theory next semester. Somehow they assigned me conformal field theory. My plan is to teach the higher dimension conformal field theory instead of 2D conformal field theory. I don't know. It depends. I don't know. It's up to the students' request. If students wants me to talk about the 2D CFT, I can use my own note. But if my current plan is talk about higher dimensional CFT instead of 2D CFT. So I will write a new note. Anyway, I don't know who is going to teach differential geometry next semester, but anyway, I'm not going to teach next semester. Okay, it's getting stronger. Okay, maybe shall we resume? I think after she comes back. Okay. Let's review. Okay, let's review. Okay. So now we move on to Raychaudhuri equation. So Raychaudhuri is the Indian physicist, and then, as I mentioned many times, so there's skepticism about black hole in the early 20s, and then Raychaudhuri, so far, so around the early 20th century, because of, I forgot, Oppenheimer, Schneider, and so on, there is so-called black hole. The notion of black hole. And also this Hubble or Hubble Lemaitre role will get a Big Bang. So inevitably we have a singularity in space-time of space-time. And there's lots of skepticism about this singularity, which is, people just discuss it's really unphysical. So. And to tackle this puzzle, so Raychaudhuri introduced so-called Raychaudhuri equation. And this will give you one step, one step towards the let the people start believing the existence in such a singularity in space-time. So that's what we are going to talk about, the Raychaudhuri equation. So this Raychaudhuri equation, it's different from Einstein equation. It's just some kind of it's called geodesic. It's called the equation for geodesic congruence. Geodesic congruence. So it's so what is a congruence? I don't know how to translate in Chinese this congruence. I don't know in Japanese there's something like I don't know. Like this way. Anyway, Chinese I'm not sure if it is.
现会.
Huh?
现会.
现会. Shen is this one.
Yeah.
会 is what?
三点水.
Can you write? Oh, okay. 好像会了，会。Okay, anyway, congruence. So which is something like this. So if you have some sigma, and from there, so you have a time. It's okay, whichever is okay. So for instance, time like geodesic, if you have like this way, like this way. If you have so any region sigma and sigma whatever prime and so on. So any region in here at any point, point P. Point P here, you have only one and only one geodesic. Okay, at any point inside this region, whatever O, There's a and only one geodesic, and which can be extended. And so this is called congruence. Geodesic. So in this time-like case, it's called time-like geodesic congruence. Okay, so then I should correct it like this way. Or I don't remember. I don't. Anyway. Time like geodesic congruence. Okay. And here we just consider, or you can have also no case. No case. It's hard to draw. I mean, it's hard to draw. But if you have something like anyway, it's really no direction. Like this way. Anyway, like this way. So this is a no geodesic congruence, and we just consider the tangent vector. Tangent vector at the geodesic is I call it C mu, and then eta is the some how to say? Is a distance between can be understand distance between the two adjacent the geodesic. It's just infinitesimal vector between the adjacent like a space. Anyway, so it's tangent to sigma. It's tangent to sigma or sigma prime, and so each constant time vector. Okay. So here I can call it this one is equal to del tau, and when tau is constant, always tau is constant surface, and then you can have eta vector, in which is tangent to this constant. Okay, and then so you can just have so they're orthogonal. So therefore, from a definition, so we just consider Lie derivative of C on eta is equal to 0. So this is the definition of the eta, can be understood as eta. And then from here, one can just conclude that the C dot nabla eta A is equal to eta dot nabla CA. So because I mean from here, so it's just this is just equal to C dot nabla eta minus eta dot nabla dot C A equal to 0. Okay. So therefore this will be hot, and this is equal to B like this way. Sorry. Hey, what I'm doing here? Yeah, sorry. This is the opposite. B, A, B. Where this, I mean, what am I doing? Okay. A, B. A? Why I'm so stupid? Okay, A, B. Yeah, sorry. So this is in fact B and B. So therefore I call it this one is equal to B, A, B. Okay, I just defined BAB, and then here, so we just consider the property of BAB by just decomposing in the and also since we have the so nabla A dot CB times CA is equal to nabla sorry, what I'm doing here? Sorry. what I'm doing here. So B dot CA and CA, and this is equal to 0 because I take the C is equal to proper time, so therefore CA is equal to -1. Yes. For time-like geodesic congruence. Okay. So therefore, this will give you BAB. CA is BA. CA is equal to 0. Okay. Or the opposite. AB and B equal to 0. That's additional constraint one can have. And then we can just okay. And then we just decouple to understand the geometric meaning of BAB. We define as follows: the 1/3 theta QAB, and then plus AB omega AB. Okay, so like this way, and then QAB is the induced metric on here. So QAB is the induced metric. QAB is the induced metric of this sigma. Okay, induced metric. So therefore, induced metric QAB is equal to GAB plus CA. CB. Okay, that's what we already learned. So in this metric is always given by the something to define the C is orthogonal to this sigma. So therefore G plus C dot C will give you the induced metric on the surface.
What is O here? O.
Sorry, theta. This is theta. This is theta. And I will explain what the theta means. So this theta is in fact, so theta can be understood as a BAB, QAB, and then sigma AB is hopefully lost. So sigma AB can be understood as a B symmetric part, and then 1/3 QAB and theta, and then omega AB is the antisymmetric part of this AB. Okay. So in some sense, this theta can be understood as some trace part, and sigma is the symmetric part of this matrix. And then omega can be understood the antisymmetric part of this matrix in some sense. Okay. And then this can be understood as 1/2 of the QAB LC. So like this way. This is anti-symmetric. Symmetrization of BAB, and then this is anti-symmetrization of BAB. So as you know, so BAB is the 1/2 BAB plus BBA, and then minus is this one. Okay, so that's the case, and the meaning of this one is as follows. So sigma AB is something like this one. So this is can be evidence of sigma. So this is how to say it's a cross sectional area of this is just this congruence. It's just moved to how is it moved to if you have the same thing here. Maybe it's better to write down like this yellow one. It's moved to this ellipsoid type like this one, ellipsoid. So that's how this is called shear. It's called shear, and the omega AB is essentially move the rotation or twist. They just rotate how the sigma is rotated. It's called the rotation or twist. And the theta is actually the dilatation or expansion. So if you have like this one, you can have small one. Okay. So change of area. So it's called dilatation, expansion, or contraction. Contraction. Okay. So that we measured. Okay. So that's what it means. I mean, it's just you can easily see, right? So for instance, BAB. So this is the most easy to understand. I mean, it's nabla nabla B. So nabla A and CB is the omega AB. And if you take the anti-symmetrization CA like this way, so this is you can easily see as a kind of rotation, right? So if you have this kind of vector field, you have this kind of vector field. It's a rotational vector, so this corresponds to rotation. And the sigma AB is the shear because symmetry. That's kind of hard to see, but theta is the trace of this one. That is the overall size. It's a trace of overall size. So the variation of theta is in fact the size of this cross sectional area. Okay, and then we just want to obtain the some relation. How does this theta, sigma, omega will change as you move along the geodesic in the space-time. So that's what Raychaudhuri think about it. Raychaudhuri think about okay. And to see that we will do the following the manipulation. C double C B A B. Okay, then which can be written as follows: CC number C. Sorry, strictly speaking, this one is equal to B A B and 1/2. And so this is a definition, and you just do the manipulation. This is equal to CC, CB, and then okay. So this is the once you just exchange nabla, you get the Riemannian tensor. That is a definition of the. As you recall, these are A, B, C, and D, and C, like this way. So if you use this definition of Riemannian tensor, you can just obtain this guy. And furthermore, we will use the equation for this the tangent vector on the geodesic. Time like geodesic, which is as follows. So this is how it acts. I forgot how to. So this one should be something like just a moment. So it should be integrated by parts. Sorry, nabla b and cc, nabla c, ca, okay? And then this is equal minus nabla b, cc, okay, it should be okay. Nabla c, ca, okay? Okay. So I just applied it, did entire thing apply into here, you get this guy, but if you act on this one, you get this one. So you have to subtract it, okay? And we know this is equal to 0. Because, did I erase? Because of this property, okay? This property, okay? We know this is equal to 0, okay? Is it okay? And then we just need to add this down. Plus this R, CBA, D, CC, CD. Okay, like this. Okay, so therefore this one can be written as the CB, BAC, like this. And then take, so contract with times QAB will give us a Raychaudhuri equation. So contract with time is CC, nabla C, theta is equal to minus 1/3 theta square minus sigma AB, plus omega AB, and then RAB, C, like this. So both contracts and QAB, you get this. So this is called this is called Raychaudhuri equation. One of the Raychaudhuri equations. So this is time like. So this is I'm not gonna R equation, Raychaudhuri equation for time like geodesic congruence. Time like geodesic. And you can again to get the other component of the Raychaudhuri equation. It's just do the same procedure here. So you just do the anti-symmetrization and the minus of this guy, or symmetrization, anti-symmetrization. That's what you need to do. And that can be written here like this way. I mean C dot nabla sigma AB. I don't want to write down everything, but the important part is that this can be written in terms of function, something like a FAB, theta, and then sigma and omega, and it contains CABCD, C6, CD, and then plus 1/2 Q, C, QB, QD, QB, RCD, minus 1/3 QAB. Oh, yeah, it's a crazy RCD. Like this way, it contains a term, something like a dot, 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 dot. Okay, so this capital C is indeed is the so-called Wa curvature, and R is a Riemannian Ricci tensor. And then here, lambda omega AB is equal to minus 2/3 theta omega AB plus 2 omega C A like this way. So those are Raychaudhuri equation. These are all Raychaudhuri equation. Okay, so the question is what this equation means. Okay? So this equation means as follows. So here, it only depends on theta and omega. So omega. So if you act, unfortunately I erased. So if you have the time-like geodesics, this is sigma, and if you have a time-like geodesic, whatever is okay. Maybe something like this one is also okay. And the sigma prime and so on. Okay. And then this is C is something like this one. Is the tangent vector, and then so C dot delta of something some tensor is equal to actually dt d tau. How this the tensor moves as you go along this time-like geodesic congruence. Okay, so this is the dd tau. This c dot nabla. So therefore here this omega is c dot nabla axon omega is the how this rotation will change as you move along this geodesic on time-like way. So as you can easily see, so if initial condition omega is equal to 0, there is no rotation in the space-time in geodesic. So the left-hand side is equal to 0. Okay. So therefore, if the initially there is no rotation, okay, no twist in the initially, so therefore, in that case, as time goes by, there is no rotation will be created by space-time. On the other hand, if you look at this one, even if sigma equal to 0, this term is clearly non-zero for curved space-time. Okay. So therefore, this shear, so shear is really like this is distortion, deformation of the sigma, will be occurred because due to this space-time curvature. Okay, that's what it means. Okay. And this theta is a cross-sectional area. So that as you move along this geodesic congruence, time-like geodesic congruence, the cross-sectional area is kind of like a contraction of this sigma, omega, and this theta. In addition to that, it also sensed. Oh, sorry, I think I should put the plus sign here. In addition to that, you have to. It also sensitive curvature of the space-time. Okay, so that's what it means about the. So about the. So about the Raychaudhuri equation. Okay, so that's what it means. Okay, and then we use this often use this first one to. First one plays very important role on the singularity theorem and so on. Okay, but before that, this is time-like one. But for new one, you have to be careful about how you define the. How you define that this QAB and so on, QAB or B and so on. Okay, let's see. Okay. Okay, so this is time-like one. For no geodesic congruence, is something like this one. So if you have something like no one, anyway, so no one like this way, and the hypersurface orthogonal to no one is something like this one. Maybe I should. I don't know how to draw, but anyway, so this is kind of sigma, our sigma. And we just draw this one, the tangent vector is k mu. And then we call this opposite orthogonal is L mu. Okay? And then this L mu itself is the no. It should be no. It's and it should satisfy the following: L dot k is equal to -1. So that's the condition we have to consider. And then the induced metric here is the new case is a bit more subtle, and the induced metric is something like a GAB and plus K A L B plus L A K B. So that's the induced metric on the orthogonal to this null vector, like this way. Okay, so that's the how it should act. Maybe I should mention. I told you wrong. So L not necessarily no, not necessarily no. So let's consider the following thing. So let's consider K mu is something like what is 1, 1, 0, 0. And then L mu can be something like what was that? -1/2. So okay, 1/2. 1/2. 1/2 -1/2. 0, 0. Is it the? No. Sorry. Sorry. What I'm doing. 1 minus 1, like this way. And if you take the inner product of the standard -1 plus, okay, diagonal. G mu is diagonal of -1 plus 1, 1, 1. Then K dot L is equal to -1. Okay, that is okay, right? K dot. So on the other hand, so L can take the following thing. L mu can take the 0, -1, 0, 0. That is also okay. This is complete space-like. Okay. L can take this kind of. Okay. So therefore, so that this is also okay. So K dot L is indeed equal to -1. So this is satisfied. Okay, so then, so we define a B as before. So B is something like a B hat, I call it, for time-like, which is something like HCA, HDB, nabla C, KD, KD, and then we decompose as before. Theta hat, HAB, plus sigma hat AB and plus omega hat AB. Okay. This way, and then we just define as follows: the theta hat is something like QAB, B hat AB, and then theta hat is no, sigma hat is the B hat symmetrization minus 1/2 theta hat HAB. Omega hat is the B hat AB, and like this. Okay, so that's the how we define the hot version, null version of theta and sigma and omega. The meaning is the same as before. So the important difference is here that the denominator used to be 3, but it's now become 1/2.
There should be AB, right, in sigma, subscript AB.
Ah, yes, thank you. Sigma AB. Yes. Like this way. And then we can just derive the Raychaudhuri equation and so on. Significantly similar, sorry. I think, yeah. I'm very sorry. This is not plus, this is minus. Sorry, this is minus. Minus sign, sorry. So the hot version is significantly similar, so I'm not gonna, so here, so, okay, I just change the null version. Null is the red one. Hot, this is 2, and hot, what was that? Hot, and hot, and K. K and K. So, and then this one, hot version of this one is significantly simple, and this one is very simple. K and K, and then minus theta, hot, sigma AB, hot, like this way. Okay, like this way. I think I need to put something here. Okay. Okay. Anyways, detail is not important. D, B, but be precise. Something like this one. C, E, D, F, and here E, F. So that's a hard version of the Raychaudhuri equation. Okay, so that's the new type Raychaudhuri equation. New geodesic Raychaudhuri equation. Fine. Any question at this moment? Okay, so then, so the point is that this is not the Einstein equation. So this is kind of more like a equation of geodetic congruent. And combined with the Einstein equation, we can have some important conclusion. So to do that, so let's first consider the time-like one. So for time like one, so I'm not gonna write down everything. So the time like one geodesic congruence equation, time like Raychaudhuri equation can be written if you combine with the how to say theta with the Einstein equation, you get the following: theta dot theta plus omega dot omega minus 8 pi. So this T A B minus 1/2 G A B T. Okay. And CA and CB. And we can assume the so-called strong energy condition. So strong energy condition is that this part is this part is the non-negative. Non-negative. So that's called strong energy condition. Strong energy condition. Condition. I will explain. Maybe I'm not sure, but I would. There is a version of a weak energy condition. It's some version of the energy condition, but this is called strong energy condition. Then it's kind of like the notch. So from here, so one can just, if you assume omega, if you assume the rotation is zero, assume rotation zero, we will get the following equation. D theta d tau plus 1/3 theta square is negative. Okay. Is negative. Okay. So this quantity, if you just move this first term to the left hand side, so then this, by assumption, this is gone. And the strong energy condition will give you this term is negative, and then sigma naught sig is of course negative. So therefore, this has to be non-positive quantity. Non-positive quantity. Okay, and the integral out this one, this theta inverse is theta 0 inverse plus tau over 3. Okay. That's the case. Okay, so that's the case. So from this equality, one can just consider the important conclusion. So if the value of expansion ratio theta like a theta, the theta at the point tau is negative on sigma, or like some sigma, which is okay, t equal to 0. Theta, so the theta 0 is actually theta at tau equal to 0. It's tau equal to 0. So that then this at some point the path satisfied tau is the less than 3 times theta 0 inverse. Okay. Then theta diverges. Okay. Theta diverges. Okay. So that's the conclusion. Okay. So therefore, if you have like some whatever sigma in time-like surface, spatial surface, you consider geodesics. The geodesic, the congruence of geodesic, and then the time is the graded. What was that? 3 times theta 0 inverse, you will see that there is something. So this how to say, the cross-sectional area goes to 0 point. Okay, so this is called caustic point. Caustic point. Caustic, or some people call it conjugate point. Point or focal point. Okay, so that's the, okay. So this is the this is called focusing theorem. Focusing theorem. It's called focusing theorem. So from Raychaudhuri equation, if you assume that the strong energy condition, so time-like geodesics really converges at a point. So that's it's called focusing theorem. And then before moving on to the new one, I just want to examine what this strong energy condition means before going to. So what does strong energy condition mean? That the so let's. Yeah, time less than actually. Time less than. Okay. And then, so this strong energy condition, so let's consider this perfect Freud. Okay, strong energy condition. So the strong energy condition for perfect Freud, what it means. Lloyd? Let's examine what it means. So the stress energy tensor of perfect Freud is, as you know, TAB is something like a rho UA, UB plus P GAB plus UA and UB. Okay, like this way. And then you just plug this one into this strong energy condition over there, and what you get is as follows. So 2 times UA CB square minus 1 rho plus 2 times UA CBA square plus 2 times P, okay, 0, like this way. And if you assume that the xc of the xc and the u are the same, u and xc are equal to xc, and then I think u xc square is equal to minus 1. Then plugging into here, what you get is that the what you get is a rho plus, so this will become 1, right? This will become 1. So therefore this will become rho, and this is become also 1. Did I make a mistake in some quotient? Seems like I made a mistake in some quotient. Where did I make a mistake? And then I want to have this one. Seems like I made a mistake somewhere. Where did I make a mistake? I don't think I can do in finite amount of time. There's some mistake in quotient, sorry. Where did I make a mistake? Sorry. Oh yeah, I found it. So this is equal to 1. So this is equal to 1. Okay. Plus 1. Okay. And this is rho times 3p. Is the greater than 0. And then this is true for of course, I mean, in the ordinary matter, so the energy density is still positive. Also pressure is, we assume positive or non-negative. So this is quite a reasonable assumption for ordinary classical matter. So that's the, some examination of this this strong energy condition. Okay. And if you use this time-like version also, it's called new energy condition. We can use new energy condition. So RAB, KA, KB is equal to 8 pi. TAB, KA, KB is greater than 0. So this is called new energy condition. Energy condition. Then the same procedure will tell you that the D theta hat, so this is new version. No focusing theorem. The lambda, so lambda is a fine parameter. Theta hat square is less than 0. Okay. So this means that the you see caustic point if it is less than 2. So this lambda is less than 2 theta 0 inverse. This means this theta hat will diverge. Okay. So that's the focusing theorem. So therefore, if you can just go back to the time into the again, so even no case. So it's a new case. It's hard to draw. I mean, it's just no like no hypersurface, and consider that like this way. It's caustic point will show up. We show up with this finite amount of time. If you go back to the past, in the at some point in lambda, a past or future is I mean it doesn't matter so much. So this is the consequence of the Raychaudhuri equation. Any question at this moment? Okay. If not, from now on, so we'll move on to so-called Penrose's the singularity theorem. But I have to introduce a bunch of notation of the space-time structure to prove that. I think, the Hawking and Penrose. I have to explain a bunch of. So maybe singularity theorem is next week. But I just introduced so-called notion of this causal structure of space-time. Okay. 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 Let's see. So we consider the so-called. Let's see. With the it's hard to, I mean, okay. So let's consider the U. That I just use some. This is U or sigma. Sigma is better. Sorry, sigma. So sigma. So I think it's better not to use the word to give a definition and so on. So if you consider space-time, space-like, this is a space-like surface, space-like surface, hypersurface, surface, and then if you consider the how to say this light cone of this one, light cone of this, okay, and then causal is the in fact in causal feature is called J plus of sigma. So this part inside it, inside here is called so it's called causal feature. Causal feature. So feature. And then here this part is called D minus of sigma. And this is called what was that? Path domain of dependence. Domain of dependence. So it's just notation. Okay. It's just okay. And then the opposite thing one can just consider. In fact, so here you don't consider a boundary. So the new part is the so only like a time like how to say time like the geodesic will be considered, and the boundary is not considered. If you include the boundary, you have to use the I instead of J. So which I'm not gonna go into the detail. I mean, if you include the boundary, you have to include the I and the and the opposite case, so this is the opposite, is you can consider opposite one, ups. Anyway, so I made a mistake, but you understand what I mean, something like that, this way. So this is called D plus of sigma, and then this part is J minus of sigma. Okay, and then the same thing. So the causal path, this is called causal path, and this is called future domain of dependence. Okay, so that's the case. The important thing is what's the difference between D plus and J plus. So for D plus case, all the causal curve has to be extended to the past, okay, to the past infinity, okay. Whereas this direction is it really can be extended to the future infinity, okay, future infinity, okay. So that's the case. So that's a notation. That's a notation. And then what we are interested in the so-called P. Yeah. Okay, and one thing is the so-called a coronal. So one notation is called a coronal. So a coronal, I don't know. Do you know how to translate in Chinese? In Japanese, it sounds like a fei shizhen. Is it the same? Most likely. Huh? It's not same.
In Chinese, it's 非边识.
非边识. How do you write 边识? Can you write? 辨识. How do you write 非辨识? Oh, okay. Is it okay? Oh, okay. It's called a corona. So this means that no timeline curve timeline curve can connect 2 points in U. If you consider that this a corona case, if you consider S1 cross R, and if you consider time direction like this way, okay? If you consider like this way, and you can consider where's the so the U is something like a so U is something like this kind of wrapping geometry. So if you consider U like this way, then timeline curve can connect these two, right? These two, point P and Q. Q in U, P and Q are inside of U, okay? So this is timeline. So but even while this U is like a space-like surface, okay? So this is not a corona, okay? Yeah. So this is not a corona. So we want to avoid this kind of situation. Okay. So this is a corona, and then I just need to introduce so-called Cauchy surface and then this global hyperbola. Okay. Okay, and then so if you consider consider that if the space-time can be written like a d plus of sigma with d minus of sigma is the entire space-time. So this is entire space-time M of G mu or whatever. If you can just write down like this way, like a sigma, and consider the like a how to say d plus of sigma and d minus of sigma, and then this sigma is called M is called then M is definition is called globally hyperbolic. Okay, so I think I should change this one. It's called, you mentioned 边系的. Like this way? Is it okay? M is called global hyperbolic, and then what's that? This sigma is called the Cauchy surface. Cauchy surface. Okay, so that's the notation of the. And then I can give you example of this Cauchy surface in Rindler Raychaudhuri state. Okay. In Cauchy surface, so if you consider the maximally extended Raychaudhuri space-time. So Penrose diagram is something like this one. Let's see. How does it work? Like this way, and so on. So this is a maximally extended Reisner-Storm case. So this, as you recall, R minus, R plus, and R plus, and so on. And then here, its Cauchy surface is indeed can be is here. Cauchy surface is this one. And here, if you consider all possible, how to say, like a extendable, like a future extendable path, consider future extendable path, it can cover D minus cover all the this how to say, the lower region, and then if you consider as I mentioned, so to define D plus, we have to consider all possible past extended causal curve. Okay, so and then you just extend it to the future. Okay, that's how we define D plus. And if you to define a D minus, you have to consider all possible future extendable. Okay. Curve, and you just it just generalizes to the past, and you consider the D plus and D minus, but in Cauchy, this can be Cauchy surface in the Reisner-Storm case. Now, as you can easily see, anyway, so if you past the extendable curve, and anyway, all possible curve can just cover in the past, like this way, and so on. So that's the Reisner-Storm case, and then, yeah. So that's one of the example of the Cauchy surface in Reisner-Storm case. And then I don't think I have a time, so I think it's a good time to stop today. But from now on, so we just consider the space-time is the acoronal, and also global hyperbolic, and some energy assumption, like whatever. I think a strong energy assumption. Also, I already forgot. Some energy assumption. Penrose proved that the Penrose proved that it's just you can have the singularity and so on. And also there is a Hawking singular theorem, which is for the universe, and then that is the I think the first half of the next lecture I will talk about this singular theorem, and then move on to what was that? ADM mass or ADM energy, and then my plan is comma integral, and so on. That is defined as some space structure, how to measure this M or energy or E, angular momentum, charge, and so on. And also, I don't know, do you want me to talk about this positive energy theorem? I don't know. I should talk about positive energy theorem. So this first by proved by Sean and Yao, famously Sean and Yao in the early 80s. Yeah, I think early 80s. And then we then give some other proof by the spinners and so on. Potentially, I will talk about this is potentially. And after that, I will move on to the black hole thermodynamics by using. if you have a Raychaudhuri equation, it's very easy to derive the black hole thermodynamics. So that's step 1 of the next week. And I think it's a good time to stop. Well, thanks for coming through for such a hard weather. It's getting worse. Anyway, so let's stop here. If you have questions, tell me.